Hello everybody. In this video we'll be going over one of the sections in chapter 6 of our text entitled Chemical Composition. So the first question to address is, why is chemical composition so important that we needed a whole chapter for it? And the reason is that everything, as we've seen in nature, is either chemically or physically combined with other substances. So it's really hard for us to measure just one thing, even though that's the thing that we're interested in. We wind up having to measure a whole bulk sample most of the time. And in order for us to know what portion of that material is the thing that we're interested in, we need to know what fraction of the material we're interested in is making up of the whole bulk material. Some examples of this would be like, you might want to limit the amount of sodium that's in your diet, right? So you want to know how much sodium there is, for instance, in sodium chloride versus something like, MSG, monosodium glutamate. So, you need to know how much sodium there is in the different things that contain sodium in your diet in order for you to get the proper amount. It's important when you're making steel, right? So steel is an alloy of carbon and iron. The different amounts of iron that you add give the different qualities of steel that we see, all the way from like a soft material to a very hard tool steel. It all has to do with the proportion of those two ingredients. The amount of hydrogen and water for a hydrogen fuel cell. So you would know what your outputs are going to be in order to produce hydrogen fuel, or even consume hydrogen fuel. You can run these either way. You can put in water and get out hydrogen, or you can put in hydrogen and get out water. And then you might need to know how much chlorine there is in your Freon. And this is important for us to estimate ozone depletion. So, for instance, this is an example that often comes up where you may not care, but somebody has to, right? Before they put this Freon out in the market, it's very important that we carefully consider the proportions and the ingredients that go into our products. In this video, we're going to be covering the mole, which is kind of a weird concept that a lot of students struggle with. It even has kind of a funny name. But it's really, if you break it down, a pretty simple concept. And I'm going to start off with what seems like kind of a silly example in order to illustrate exactly what a mole is. So you may have ran into this situation before. You go and you need a certain number of nails for a project, but you go to the hardware store and they're selling nails by the pound. You'll actually see that a lot, where they sell nails by the weight. So the question you have is, how do I know how many nails I am buying when I buy a pound of nails, right? There's not exactly a conversion chart up there. And really what this is it's an analogy for how many atoms are there in a given mass of an element. So if I have 12 grams of carbon, if I have 13 grams of carbon, how many atoms is that? So let's go through an example where we are able to count the number of nails by being given a weight. So a hardware store customer buys 2.6 pounds of nails. Okay, a dozen nails has a mass of 1.150 pounds. And the question is, how many nails did the customer buy? So we start off with a fact that's given to us in this problem here. Okay, we know that 1 dozen nails has a mass of 0.15 pounds. So 1 dozen nails equals 0.150 pounds. And we know that there are 12 nails for every 1 dozen nails. So that means that if we take the pound of nails, right, and we multiply it by this conversion factor, which we built on this fact, just like we were doing with our conversion factors before, we'll know how many dozens of nails we have. And then if we multiply that by 12, and cancel this unit here, this dozens of nails, we'll know the number of nails that we have. So let's see what that looks like mathematically. So we start off with the amount of nails that we had, the weight of it. We know that there's 0.150 pounds for every 1 dozen nails. And we know that there are 12 nails for every 1 dozen. If we look at these units, we can see that they're canceling now. And we get a total of 208 nails, right? Because it canceled every other unit in this. So that means that in 2.60 pounds, there are 208 nails. And we've managed to count the nails by weighing them. So let's do a little thought experiment here. What if he bought a different size nail? Would the mass of a dozen still be 0.150 pounds? No, right? If he bought smaller nails, then you'd get more nails in that amount of weight. If he bought larger nails, then you would get fewer nails, right? Would there still be 12 nails in a dozen? Yes, right? There's always 12 things in a dozen. That's what a dozen is by definition. Would there be 208 nails in 2.60 pounds? No, right? If you bought larger nails, you would get fewer nails for that weight. If you bought smaller nails, you'd get more nails for that much weight. And how would this affect the conversion factors? So our 1 to 12, 12 nails to a dozen, that would be unchanged. But our number of nails our number of our weight that makes up a dozen nails would change. So let's bring this analogy back and see how we can use the mole and atoms to count the number of atoms in a certain mass. So just like we found out that there was a certain mass of nails that is equal to 1 dozen, if we can find the mass of a particular number of atoms, we can use this information to convert the mass of an element sample to the number of atoms in the sample. So we need that equivalent of X number of atoms is equal to X number of mass, right? The number of atoms we will use is this huge number, 6.022 times 10 to the 23rd, okay? This is called Avogadro's number. And if we have that many things, we call it a mole. All right, that is no different than when we call 12 things a dozen. All right, now this is a really huge number, but you shouldn't let that surprise you, really. We would have, because the atoms are really, really small, you would need a whole lot of them in order to be able to weigh them and have that be any significant amount of mass, right? So we would need some kind of really big number when we're talking about atoms. Now it's a really odd number, but I'm going to show you why it is that we chose this one. It actually makes things work out very conveniently for us. But first, I do want to recognize that we now have a new fact here. 1 mole is 6.022 times 10 to the 23rd things. So that means that we have 2 new conversion factors that we can play with. We have that there are 6.022 times 10 to the 23rd atoms in 1 mole. Here I'm using atoms, but it could honestly be anything. You could have this many kites in the sky. So it's really just a universal conversion factor. And we have the inverse, right? 1 mole for every 6.022 times 10 to the 23rd atoms. So the reason that we use that crazy number is because it just happens to be that 6.02 times 10 to the 23rd is the number of things equal to the number of atoms in 12 grams of C12. You might remember that when we were talking about the periodic table, we used C12 as our baseline. We understood carbon really well, and we said that this one specific isotope of carbon weighs exactly 12 AMU. Okay, and that was our definition and our basic metric that we used to give the mass values to all the other elements in different isotopes. If we have 1 mole of C12, then that means that that weighs exactly 12 grams. Okay? So what this allows us to do, what it basically has done, is it's made the unit AMU synonymous with the unit grams per mole. Okay? And I want you to keep that in mind as we go through. So now, if I want to know how many grams a mole of any element weighs, all I have to do is go to the periodic table and look up its atomic mass. Okay? And it makes things a lot easier for us to figure out how much a mole weighs. Okay? And grams are a fairly simple unit that we can measure in our real world, whereas AMU are really, really tiny units that are difficult to work with. Okay? I'll also mention that we've talked about formula mass already. We can extend this past the periodic table and elements into compounds, where it will also be true that the formula mass of a molecule, that AMU is still going to be equal to grams per mole of that compound. Okay? So the logic also extends that if they're in 12 grams, there's 1 mole, that there's 6.022 times 10 to the 23rd atoms in that, because that's how many atoms there are in a mole. Okay? Let's take a look at a problem and see how we can start applying what we've just learned. So a silver ring contains 1.1 times 10 to the 22 silver atoms. How many moles of silver are in the ring? So we're given a number, 1.1 times 10 to the 22 atoms of silver. And we're asked to find the number of moles. Our solution map goes straight from atoms to moles. And the reason being is that we have a fact here that 1 mole is 6.022 times 10 to the 23rd atoms. Which means we can use one of our conversion factors to go from the atoms that we have here to the moles that we need. We will place atoms in the denominator because that is the unit we want to cancel, and we'll place moles in the numerator because that's the unit we want in our final answer. We put in the original value that we had, atoms of silver. We have our conversion factor down here. We end up getting this number when we type it into the calculator, but we were limited to 2 sig figs for this by this number here, so we round it to 1.8 times 10 to the negative 2 moles of silver. If we pay attention to our units, we see that we canceled our atoms and we were left with moles. And our final unit has moles, and we can put a little label of silver there so that we know what what moles we're talking about. If we do a quick check, we'll see that this number was less than Avogadro's number, right? Avogadro's number is times 10 to the 23rd. This is times 10 to the 22nd. It's a smaller number, okay? Therefore, we should have gotten less than 1 mole, right? Because 1 mole is times 10 to the 23rd. We had fewer than that. This should be a number smaller than 1 mole. Okay, so now that we've gone from the number of atoms to the number of moles, let's see if we can do this the opposite way, and if we're given the number of moles of a certain substance, that we can calculate the number of atoms that we have. So here we're started off by being given the number of moles, 2.45 moles of copper, and we're being asked to find the number of atoms. Our solution map is the opposite of what it was before. Now we're going from moles to atoms. We use the exact same fact though, because that's what's relating moles and atoms. But our conversion factor is going to be the inverse of the one that we used before. Now we need to cancel these moles and we need the units of atoms. So atoms go in the numerator, moles go in the denominator. When we do our math out, we get our original value, 2.45 moles of copper. We're going to cancel our moles, and we get out the correct number of atoms here. And we do a little check here. This number should be larger than Avogadro's number because we had more than 1 mole to start off with. And Avogadro's number again is 10 to the 23rd. This is 10 to the 24. So that number makes sense. So now we've mastered going between moles and atoms and moles. Let's start talking about the relationship between moles and mass. All right. So we have learned that the mass of 1 mole of atoms is called the molar mass, or formula, and for a molecule, it's going to be the formula mass. The molar mass of an element in grams is numerically equal to the element's atomic mass in AMU. Okay, that is the same thing as what I said before about the units. AMU is a synonymous unit with grams per mole. It follows that the lighter the atom, the less 1 mole of it would weigh. Okay, if I have a package that holds a dozen baseballs, okay, or say like a bowling ball, right? Well, if I have 8-pound bowling balls in there, that's going to weigh less than if I have 12-pound bowling balls in there, okay? The lighter the atom, the more atoms there are in 1 gram. Okay, that also follows, right? If each atom weighs less, you're going to need more of them to make up 1 gram. So I think it's useful to look at this in a table to kind of think about what we're talking about. All right, so if I had hydrogen, our lightest element, I'm always going to have the same number of pieces in 1 mole, the same number of atoms in 1 mole. Just like I always had 12 nails in 1 dozen, I'm always going to have the same amount of that. But each one's going to weigh a different amount, okay? This hydrogen is going to weigh 1.008 grams. Carbon's going to weigh 12.01 grams, okay? So on and so forth, where each of these are the same as their atomic masses if you look them up in the periodic table. Okay? And visually you can see that, for instance, a heavier atom like sulfur is going to visually be larger than a lighter atom. 1 mole, that's going to be visually more than 1 mole of carbon because it's lighter. So let's try a problem here. We want to calculate the moles of sulfur in 57.8 grams of sulfur. Okay, so we're given the mass of the sulfur, 57.8 grams per sulfur. We're asked to find the moles of sulfur. A solution map is just going to be to go directly from the mass to the moles of sulfur. But first we need to know how much 1 mole of sulfur weighs. To do that, we have to look up its atomic mass in the periodic table. Okay, so you'd find that 1 atom of sulfur is equal to 32.07 AMU. So 1 mole of sulfur is going to equal 32.07 grams. From that, we can get our conversion factor. Again, we're going to pay attention to how we set this up, okay? The answer we want is moles. It goes in the numerator. The value we have is grams. It's going to go in the denominator. We take our original mass. We multiply it by our conversion factor, 1 mole for every 32.07 grams. And we get that out that there's 1.80 moles of sulfur. If we do a quick check, okay, we knew that in 1 mole there was going to be 32 grams. We had more than that, so we knew that we should be getting out more than 1 mole. And that makes sense. So let's do a practice problem and see if we can go the other way with it. if we are given the number of moles of carbon in a pencil lead, can we figure out its mass? So we're given in our problem that we have 2.21 times 10 to the third negative 3 moles. And we're asked to find how much mass of carbon that is. Our solution map is the opposite of what we had before. We start off with moles, and we got to find our grams. And our conversion factor that we're going to need, our fact that we're going to need, is going to come from the periodic table, but it's the same form as we had before. Okay, we know that 1 mole of carbon is equal to 12.01 grams. We set up our conversion factor again so that it has the unit that we want in the numerator and the unit we want to get rid of, moles, in the denominator. When we plug it in and apply our conversion factor, we start off with the number of moles that we were given of carbon, and then we're going to multiply that by our conversion factor. We'll cancel those moles, and we wind up with 0.0265 grams of carbon. If we do a little check, we started off with quite a bit less than 1 mole, and we knew that 1 mole was going to weigh 12 grams, so it makes sense that we got this small number, quite a bit less than 12 grams of carbon out.